Okay, so, you know, we've kind of been, I think, talking a little bit about these concepts from the beginning. I mean, the very motivation for us sort of discovering what the derivative of a function is was looking at the slope of a tangent line. We've already been using the language of, oh, this is increasing, so its derivative is positive, or this is decreasing, so its derivative is negative. And a lot of that is going to be used in this curve sketching. I want to say right up front that, like, curve sketching is going to feel like not an application. It's going to feel like something I don't need to do. You're not going to be asked to sketch a curve in the wild. Like, I get that. However, curve sketching is sort of a proxy for actually just understanding the behavior of a function, like a whole function, like what its behavior is like at various points in its domain. And so for that reason, it is, you know, valuable. And then in the next, well, we're doing this for 2 sections. In the last section, we're going to do these optimization or applied maximum and minimum problems. And that's where we kind of take a look at, you know, use some of the skills that we did with curve sketching, but then just zero in on the one particular type of question that we want to be able to answer. So we'll begin with just kind of reminding ourselves, again, what the derivative tells us about the behavior of a function. Over here, if I've just drawn a tangent line over on that side. So the slope is positive, right? Increasing. And that means that the derivative is positive, right? Derivative is going to be greater than 0. In the middle, I pick some point in the middle here. I draw that. Here, the function is decreasing. Slope is negative. The derivative is negative. Again, over here, you know, the function is increasing. So the slope, and thus the derivative, is positive. Right? There is a one-to-one correspondence between a function having, you know, being increasing and its slope and its derivative being positive, and decreasing and its derivative being negative. If I was interested in, if I wanted to know where is this function increasing for what values of x, what I want to do is look at the derivative and then see if I can't figure out where's the derivative just positive, right? If I want to know where a function's decreasing, I want to figure out where is that derivative negative. And we're going to begin just by trying to answer that question.
So in that, the diagram though, the graph, whatever, so it'd be like for the first one, it would be between negative 1.5 and negative 0.5 is where the slope would be.
I mean, it would be from, I would say, negative infinity, it looks like. I would have to infer what it does beyond this point, up until it gets to that peak, which could be about, you know, maybe it's actually could be a little bit over here.
And then negative until.
And then from here until here, I'd expect that a derivative is going to be negative. And then from here until it looks like maybe forever, the derivative is going to be positive again. But like that's a really good question, because like one of the things we're going to be able to figure out is, you know, you look at this graph. Obviously, we're only presented with the graph on some window, right? This goes from like minus 1.5 to 1.5 on the x's. Like, how do I know that somewhere over here it doesn't like turn around again and I just haven't graphed it, right? We can actually answer that question definitively if we use calculus. You know, we won't have to worry about, have I not looked at this, viewed this on the right window? Because, as this theorem states, if a function is continuous and differentiable on some interval, then if the derivative is greater than 0 for all values of x in that interval, then it's increasing on that whole interval. If the derivative is negative for all values of x on that interval, then it's decreasing on that interval. We'll have separate theorem to address what happens when the derivative is 0, but we've sort of kind of nibbled at the edges of that question already in class. So we're going to figure out, oh man, I love this. I love these problems. Okay, because we do one of my favorite things ever, which is we're going to make a sign chart, like SIGN chart, which is like super simple to do. Like if we can remember that if I get a positive if I multiply two positives or two negatives, and I get a negative if I multiply a positive and a negative together, then a sign chart is like super easy, right? We're going to be able to answer these questions pretty simply with doing almost no calculation. Okay, it's a beautiful thing. So we're looking at the function x cubed minus 3x squared, and we want to know where is that function increasing and where is that function decreasing. So I know that if they're asking me about increasing and decreasing, what is it that I need to look at? The derivative. The first derivative is going to answer that question for me, or help me answer that question. So let's find the derivative. We're going to find the derivative and find where that derivative is positive and where the derivative is negative. So f of x is x cubed minus 3x squared. What is f prime of x?
3x squared minus 6x.
Now, here's what we need to understand, is that in this particular form, the derivative is not very useful to me. So what I'm going to do first is factor it. Factor that derivative. I want to be able to see it, I hope ideally, as a product of linear factors, meaning factors that only involve x to the first. Sometimes we can't go like that simple. Like sometimes with some functions we might have to involve like quadratic factors, and that's okay. But here we definitely can, right? Like, let's factor out a 3x. And if I factor out a 3x, then what we're left with is x minus 2. It is absolutely crucial that we factor it.
Let us know where it's will be negative and positive.
It will let us know. Immediately, the first thing we figure out first, though, is where it's 0, right? And that's figuring out where it's 0 is like super easy when the derivative is factored. Say it again.
X equals 2.
And 0. Yep.
Okay.
So f prime of x is 0 when x is 0 or 2. Now here's how we use this information. We're going to have to do no arithmetic, no calculating. It's almost going to solve itself at this point. We had to do a bunch of work to get to this point. Like, I'm not saying that there's no work involved, but we're going to make a sign chart for f prime of x. So it looks like this. I have a vertical axis and a horizontal axis. Along the vertical axis, I'm going to have a row for each of the factors. So I need a row for 3x. I need a row for x minus 2. And those are the only factors. So then my final row is for the product, 3x times x minus 2, which is, of course, the derivative itself. The horizontal axis is the real number line. So what I'm gonna use that horizontal axis to mark these values, but because it's a real number line, I have to actually put them in order. Like, I can't be haphazard about it. So 0's got to go first, and then 2. So what I'm going to do next is we're going to fill out the row for 3x, and then we're going to fill out the row for x minus 2. The only thing we care about in filling out the row is, where is it 0? And then on each side of 0, is it negative or is it positive? So 3x is 0 when x is 0. That part's easy. Now if I throw in something that's less than 0, 3 times x is going to be negative. If I put in a negative, 3x is a negative. And if I put in a positive, 3x is a positive. I don't care what positive number or what negative number they are. Like, that is immaterial to me. Is it plus or is it minus? And then I'm going to do the same thing for x minus 2. This is the reason we love it when there are linear factors is because if you have a linear factor, there's going to be precisely one spot where it's 0, and then on one side of that 0, it's going to be only positive or negative. You know, on the other side, it'll be only positive or negative. Like, it switches from one side to the other. And that's always true if you have a linear factor. So x minus 2 is 0 when x is 2. If I plug in something less than 2, what is the sign of x minus 2?
Negative.
It's negative. You know, like I do it for instance, like if x was 0 and I plug it in, like clearly 0 minus 2 is negative. It's going to be negative on that whole side. If I plug in something that's bigger than 2, what do we get? Positive. Okay, now the last row is going to practically fill itself out. This is just the product. This last row is the result of multiplying these two rows together. So I know that it'll be a 0 when either of its factors is 0. So I'm going to mark those down. So now I've partitioned the real number line into 3 intervals. On the left side of 0, when x is less than 0, what's the sign of the product? 3x times x minus 2. Positive. Right? It's a negative times a negative. It's a negative times a negative, so that's got to be a positive. In between 0 and 2, negative because it's a positive times a negative. How about on the other side? We had to plug in 0 numbers to the derivative.
Nice.
We had to do no calculating. All we need to remember is that if I multiply two numbers of the same sign, I get a positive. If I multiply two numbers that are different signs, I get a negative. Now, look at this sign chart. Tell me, where is f of x, the original function, increasing?
Less than 0 and over 2.
Yeah. So 2 different intervals, right? We could write them as inequalities, as I've just done. You could also write them as intervals, so less than 0 would be like negative infinity to 0, and so we call that a union, but you could just also write and, or actually, 2 to infinity. And f of x is decreasing where? Yeah, so that's 0 less than x less than 2, which you could also write in interval notation, 0, 2. Now, if I look at a graph of this function, I'll see that it turns around. Like, it'll look something like this. I'm not going to be super accurate with like where things occur, but so I'm not going to put any markings exactly on this, but like it'll look something like, actually, here's what it'll look something like this. Now, I know that below this value, it just keeps, like, this is increasing forever, right? I know there's not going to be any other point where it turns around and starts increasing again, because if it did, I would detect another value where that derivative is 0, and I would have detected that it's decreasing on some other interval, right? This sign chart describes perfectly that kind of behavior. So I know it doesn't turn around again and start decreasing again, like on the other side here either. Now, we figured out where it's increasing and decreasing just by looking at where the derivative is positive and where the derivative is negative. This begs the question, though, really, what's going on when the derivative is 0? What's going on when x is 0 and when x is 2 in this? Values for which the derivative is either 0 or undefined, we call those critical values. If we're looking for a maximum or a minimum, a relative max or a relative min can only occur when the derivative is 0. So what we mean by relative maximum is that, like, if we look at, say, this graph, this right here is a relative maximum, meaning, or also called a local maximum. It's a maximum relative to the points surrounding it. There might be points that are bigger, right? Like this thing, it's not like an absolute max, because this function will just keep going and going and going. But it's bigger than anything, like we would say, in the neighborhood of this point. And for the points around it, it's a maximum. And if you're going to have a local max or relative min, can only happen where the derivative is 0. Now, finding where the derivative is 0 tells you where you can have a local max or a local min. But if you find where the derivative is 0, like, we don't know if it necessarily is a local max or if it is a local min. Like, not just by seeing where it's 0 can we say, oh, that's definitely a local max or that's definitely a local min. Like, it could be one or the other. It can't be both. It's possible it could be neither. And so, like, if we actually have a local max, so if we look at this figure right here, I'm just going to impose some axes. So let's say that this local max occurs at the value C. I'll call it C for critical value. Definitely up here, right, the derivative at C is 0. What is the derivative over on this side? What can we say about the derivative on this side? Yeah, it's greater than 0. It's got to be positive. What about on this side? Yeah. So this point, C, f of C, is a maximum when the derivative, f prime of x, goes from positive to 0 to negative. We're looking for a sign change in the derivative. We need the derivative to be 0, but it has to get to 0 in this manner. Positive, 0, negative. Increasing, leveling off, decreasing. That's how a maximum occurs. On the other side here, again, if we call this point C for critical value, then down here at the minimum, definitely, f prime of C is 0. But what can we say about the derivative on this side, to the left? Yeah, the derivative is negative on that side. On the right side, the derivative, the function's increasing, so the derivative has to be positive. So that means that the point C, f of C, is a minimum when f prime of x goes from negative to 0 to positive. Like, if we're looking for a minimum, we're looking to see that the derivative becomes 0, but it needs to become 0 in this fashion, right? Decreasing, negative, leveling off, increasing. Negative, 0, positive. Now, if we go back and re-examine the sign chart that we made, and I've reproduced that sign chart here in the notes. This is what our sign chart looked like. We've already done all the work we need to do. All the work we needed to do to figure out where's the derivative positive, where's the function increasing or decreasing. We can reuse that work to figure out, do we have any maxima or minima, and where are they? So we want to focus on this information here, right? These parts of the graph. Those are our critical values. So let's look at the 0 first. When x is 0, do we think that'll give us a maximum or a minimum, or do we not know?
Maximum.
Why maximum?
It goes plus to 0 to minus.
Yep. Now, we wouldn't say that x equals 0 is a maximum. It gives a maximum. Because when we talk about the maximum or minimum value, we're talking about the function values. So if we want a maximum, if we were doing a problem that says find a maximum value, find where any maximum values occur. Finding where they occur is different than finding the actual maximum values. If we want to find the maximum value, we have to take this number, plug it into the function. the actual maximum or minimum that we would be looking for would be the function evaluated at that point. So let's find that y coordinate. So f of 0, that one's pretty easy to find. 0 cubed minus 3 times 0 squared is 0. So that means that the point 0, 0 is a max. And that's sort of a kind of nice complete way to answer the question. When we give the coordinates, both coordinates of the point, we're saying not only do we know where it occurs, but we know what that maximum value is. Now, what about when x is 2? What do we think is happening there? It's a minimum. Yeah, exactly. So x equals 2 gives a minimum. I mean, I kind of, when I make these sign charts, I kind of almost just sketch in, like, f prime of x is increasing. So that means the graph has to look like this. Then it levels off, and then it's decreasing. You can just see, like, the maximum and minimum kind of occurring. Like, obviously it doesn't look quite as boxy when you're graphing it, but, like, that's the overall, like, rough behavior of the graph around these points. So let's find that y coordinate. F of 2 is 2 cubed minus 3 times 2 squared, which is 8 minus 3 times 4. 8 minus 12 is negative 4. So that means the point 2, negative 4 is a minimum. Now this problem then says use this information to sketch. Now our sketch may not be perfect, but it'll actually be pretty serviceable given, you know, the fact that we're just looking at the first derivative to help us out with this. You'll notice I'm going to plot just 2 points. The 2 points that we found. We know that 0, 0 is a maximum. And let's see, let me put a scale on here. Say 1, 2, and then 1, 2, 3, 4, negative 4. So 0, 0, I know it goes through 0, 0, and that's a maximum. So right off, I'm just going to be like, oh, that's what a maximum looks like. You know, there's what my sketch looks like so far. And then this point 2, negative 4 is a minimum. That's what a minimum looks like. But you know what? Because of the sign chart, I know that heading into that max, it's like increasing the whole way. There's nothing it can do but increase into that. In between, it has to be decreasing the whole way into this curve, and then get ready to change direction, and then heading out of it, it's increasing and it stays increasing. It's not a perfect sketch. Like, I didn't find this other, you know, x-intercept, so I could certainly do some algebra, you know, if I wanted to help with that process. If I wanted to kind of just make it a little bit more precise. Also, as we'll find out, knowing that a function is increasing or knowing that a function is decreasing will help us sketch, but it's not the whole picture, because like a function could be increasing in 2 different ways. You know, like a function could be increasing like this, or it could be increasing like this, and those are wildly different types of behavior. Right? So we did have to do a little bit of inference that, you know, and without plot, but if you look at the graph, and given that we plotted precisely 2 points, it's actually a pretty serviceable graph for the amount of work that we had to do to get to it. Most of the work, to be honest, is probably listening to me talk about it at length. And I appreciate your patience. So when we use that first derivative, like we just did here, you know, we used our sign chart for the first derivative to figure out whether a critical value was a maximum or a minimum. You know, we said, oh, the derivative's going from positive to 0 to negative. That means it must be a maximum. We call that the first derivative test for maximum and minimum. And as its name suggests, there's a second derivative test for maximum and minimum. We'll look at that in a little bit. But first, let's just do another one of these. Let's find the relative max and min for this function. Now, they didn't say give the intervals on which it's increasing or decreasing. We'll probably find it just on our way. We don't have to state it, though, right? Because we're going to make a sign chart. We'll have all the information if we wanted to see where it's increasing or decreasing. But we're just going to make that sign chart and then kind of pluck out the information we need to identify where the maxima and minima are. So we're going to find y prime. So y is 3x to the fifth minus 5x cubed. What do we get for the first derivative?
15x to the fourth
Mm-hmm.
minus 15x to the second.
Yeah.
Equals to 15x to the second.
Say that again?
Doesn't that just get us 15x to the second?
No.
No, but we can.
'Cause we're not-
factor out 15x.
But we can factor out a 15x squared. And in fact, we need to. The derivative written in this form is not very useful to us. It's only when the derivative is factored that we're going to find that we can do anything with this at all. So let's factor out a 15x squared. What's left inside? X squared minus 1. Now when we factor, we really just want to factor all the way. So let, yeah, close. X plus 1, x minus 1. Yeah. That's a difference of squares. And when we've found this first derivative and we have it in factored form, this is where it's at. We can actually find the critical values, right? So what are the critical values?
1, -1, and 0.
Mm-hmm. So y prime equals 0 when x is 0, -1, and 1. And since I think we're probably going to need them, let's go ahead and just find the y coordinates. When x is 0, what's y? 0, yep. When x is -1, let's see. Because they're odd powers, -1 to an odd power is still -1. So that would be 3 times -3 plus 5. So positive. What's that? So we're plugging them into this, the original?
Oh, okay.
Yeah, because we're looking for a y coordinate. Like if we plugged them into the derivative, we should get a 0 in all of this, right?
Right.
Yeah,
That's
okay.
okay.
So we're plugging them into the original. So if x is -1, then x cubed and x to the fifth are both -1. So we get -3 plus 5, which is 2. And if x is 1, x to the fifth and x cubed are both +1. And so 3 minus 5 is -2. So we found the derivative, we found our critical values. What's next in this process? Sign chart. I love how you said that with such like conviction and confidence. Sign charts are gonna, or I don't know. I find them very enjoyable to make. Like, you know, like I like when things can be simple. You know, where is x positive? X is positive when x is positive, right? Where is x plus 1 positive? Oh, I think I can figure that out, right? If I can just like, I kind of just take out these elements of the derivative and make them as simple as possible. So the sign chart, I need to make a row for each of the factors. So a 15x squared, x plus 1, x minus 1, and then their whole product. I could write it out as the product. I'm just going to call it y prime, but I know because I know that's what I get when I multiply all three of them together. We love it when we have linear factors, x plus 1, x minus 1. Those are linear factors because with a linear factor, it's always 0 in precisely one spot, and then all negative to one side and all positive to another side. So I just have to figure that part out. This part up here, the 15x squared, is not linear, but I think we're going to be pretty good at figuring out where that's positive and 0 and where it's negative. So along the horizontal axis, that's the real number line. So I just have to take my critical values, put them in order. So -1, 0, and 1. Where's 15x squared? 0. 0. What is it on the left side?
Went negative.
No, positive. Negative times negative.
Yeah.
Just square.
Right, it's x squared. So it's always going to be positive. In fact, it's positive everywhere except where it's 0. X plus 1, where is that 0?
-1.
-1. What is this doing when I plug in values less than -1? negative. What is it doing when we plug in values greater than -1?
Plus.
Yeah. X minus 1, where is that 0? 1. If I plug in something less than 1, negative. On the other side? Yep. I could do these all day long. Now let's put this together. Where is y prime 0?
-1, 0, 1.
Mm-hmm. And notice in filling in our zeros, we've kind of partitioned the real number line into these 4 intervals. And we're just going to consider each interval and go in order. What's going on when x is less than -1?
Negative.
Why?
Because you're multiplying a plus and a positive and a negative.
Well, we're not just doing that. We're multiplying a positive and a negative. So that product is positive.
Okay, I see.
Or sorry, that product is negative. And then we multiply that by another negative.
Okay.
So that whole product is positive. In fact, if you have lots of rows, just count up how many negatives. If you have an even number of negative rows, the whole thing is positive. If you have an odd number of negative rows, the whole thing is negative. How about in between -1 and 0? Negative. How about between 0 and 1?
Also negative.
Also negative. And how about on the other side? Positive. Okay, let's identify where do we have a maximum?
-1.
When x is -1, because it's increasing, it levels off, and that's decreasing. So we want to say we have a maximum when x is -1. If we're giving the maximum value, we want to make sure that we include the y coordinate. So we could just give it as a point. The point is -1, 2. Any other maximum values?
Yeah, 1. No, that's a min.
That's a min.
1 is
Who wants to support their answer?
goes from a negative to a 0 to a positive.
So what does that mean that it starts out negative?
It's a min. Oh,
Okay, decreasing, right? So when the derivative is decreasing, right? When the derivative is negative, it's decreasing. It levels off, and then it's increasing again. So we have a minimum at +1. It is.
oh.
So minimum at 1, -2. What's going on at 0?
Just going down.
Just going down, right? So we don't observe a sign change. So this is neither a max nor a min, because no sign change in the derivative. So, like behavior like that, if we looked at a graph, could look something like, I don't know, let's see. Like it's decreasing and then it kind of levels off and becomes decreasing again. Like that could be the type, you might see something like that. It's not the only way that you could see that happen, but there's an example where you could have a 0 derivative and it not actually, coincide with a maximum or a minimum. First derivative. Now, we know when a curve is increasing and we know when it's decreasing by looking at its first derivative. But a curve could be increasing in different ways, right? Here's an increasing curve, and here's an increasing curve. Their behaviors are very different, though, right? And so just looking at the first derivative doesn't really tell us which one of those scenarios it is. So we would say that this one on the left, we call this a concave up shape. On the right, we call it a concave down shape. These are 2 increasing curves, but you could also have decreasing curve that's concave up. So decreasing that's concave up looks like this. Decreasing that's concave up, concave down looks like this. Right. So the concavity of a curve kind of tells us how it's increasing or decreasing. So we're going to look at how we could determine that. And on the next page, here's a concave up shape. I don't care that it's increasing so much, just observing that it is concave up. And you see there's these little tangent line bits that are drawn. So I could see, look, here's a tangent slope that's a little negative, slightly decreasing. Then the tangent slope becomes positive, and then it's even more positive. So what's happening to f prime on that interval?
Decreasing.
What's that?
It's decreasing. on
The first derivative is decreasing
uh,
because it goes from negative to positive.
I'm looking at the right one. Nope. Probably not.
On this definition, right? So here's a tangent slope, a little bit negative, then it's positive, then it's even more positive. What's happening to those slopes? What's that? They're actually increasing. Right? If something goes from negative to positive, it's increased. And then it went from positive to even steeper positive, right? It got bigger. The first derivative is increasing. And now think about f prime just as a function in and of itself. If f prime is increasing, what's happening to its, what can you tell me about its derivative?
If f prime is increasing, then we assume that the second derivative is also increasing.
We don't assume that it's increasing, no. But there is something we know about the derivative of f prime. What can you tell me? Let's remove this prime-like vocabulary from this question. And let's just think about what we did last time. If a function is increasing, what can you tell me about its derivative? Nope, its derivative is... What's that?
It's at its first level.
Well, I guess its derivative is a first derivative, but there's something for sure you could tell me.
It's greater than 0.
It's positive,
Yeah.
right? When a function is increasing precisely when its derivative is positive.
Well, no, I meant like the first derivative is always going to be higher than like a lower derivative, right?
I don't know, not always greater than. I mean, if you want to just look at powers and you're looking at just polynomials, I guess you could say that a derivative will have a smaller power of x. But when we're talking about the behavior of the function, this is what we spent like most of Monday's class on. That's why we make this sign chart, right? If I want to know where f is increasing or decreasing, I just look at where the derivative is positive and negative, right? That's why we make the sign chart. So if f prime itself is increasing, then its derivative, which is f double prime, is positive, is greater than 0. At this figure on the right, we've drawn in some, tangent slopes here. What's happening to f prime? What's happening to those tangent slopes? They're decreasing. So what can you tell me about the derivative of f prime? Yeah, it's got to be negative or less than 0. So we can actually tell a lot about the concavity. We'll know about not just whether a graph is increasing or decreasing. We can tell whether it's increasing or decreasing by looking at the first derivative. We could tell how it's increasing or decreasing. Is it increasing concave up or increasing concave down? Is it decreasing concave up or decreasing concave down? By looking at the second derivative. Now the other thing we could put together is that, let's look at these, I'm just going to I'll draw it up here in the margin. This is what a max looks like, right? This is what a min looks like. At a maximum, is it concave up or concave down?
Concave down.
That's a concave down. And how about at a min? Concave up. So if I know that the first derivative is 0 and I know that the second derivative is negative, I know that that's got to be a max, even without making a sign chart for the first derivative. If I know the first derivative is 0, right here, that horizontal tangent line, if I know the first derivative is 0 and I know that the second derivative is positive, it's got to be a min, because it's got to be concave up. Even without making a sign chart for the first derivative. And that is what is stated down here. We call this the second derivative test for maxima and minima. So whether you make a sign chart for the first derivative or test the concavity at a critical value, you'll always get the same consistent conclusion. You'll never see a case where using the first derivative test you find something's a max, and using the second derivative test you find that it's a min. If that happens, there's an error in your work somewhere, right? And we should find it. So let's take a look at, let's do an example. Let's examine concavity. We're going to figure out where this function is concave up and where it's concave down. So they gave us the function x cubed minus 3x. Now, if they're asking me about concavity, I know I need to find the second derivative. So I find the first derivative first. 3x squared minus 3. Second derivative is just 6x. It's already factored, not a whole lot to do there. This is going to be a super easy sign chart. And we do the same thing. If we're looking to answer questions about concavity, we're still going to make a sign chart to answer questions. A sign chart for the second derivative to answer questions about concavity is analogous to making a sign chart for the first derivative to answer questions about where is it increasing or decreasing. So the bottom is a number line, right? That's our real number line. What value or values am I interested in there? Yeah, 0 is the only place, right? Where this the second derivative is 0. Where the second derivative is 0, we don't really give it a special name. They're not called critical values, but it certainly is a point of interest for us. So I know that the second derivative is 0 there. If I plug in values less than 0, we'll get negative. If we plug in values bigger than 0, we get a positive. And so now just looking at this sign chart, we know that the graph of y equals x cubed minus 3x is concave down when x is less than 0 and concave up when x is greater than 0. I know what you're all thinking. You're thinking, but what about when the second derivative is actually 0? So we can kind of tell just by looking at our sign chart, when the second derivative is 0, that's like some point where the graph is going from concave down to concave up. And any point in the graph where the concavity changes in either direction is called an inflection point. So we can detect inflection points by setting the second derivative equal to 0 in much the same way that we can detect maxima or minima by setting the first derivative equal to 0. So let's find the inflection points. It's the same function, x cubed minus 3x, so I'm just going to repeat, there was the second derivative that we found. Here's the sign chart. So we see a change in concavity. That means that we have an inflection point when x is 0. And so it's an inflection point. So just like when we find the max or min, we want to find both x and y coordinates. With inflection points, we want to find both the x and y coordinates. So when x is 0, we'll get that y coordinate. 0 cubed minus 3 times 0. Not a whole lot of math to do there. So we have an inflection point at 0, 0. Sometimes in a graph, an inflection point really kind of stands out. Like it's almost like if you look at a graph of y equals just plain old x cubed, it does something like this. And there's almost this like flattening out there in the middle. Like if you did the same thing for just the function y equals x cubed, you'd also find that 0, 0 is an inflection point. And you kind of see it kind of flatten out. Like that sort of, to me, feels like a really noticeable inflection point. Sometimes they're a little bit more subtle. And if you look at the graph below, here's our inflection point right there. So there's not like a huge noticeable change happening in the graph. Clearly we could see it goes from a concave down shape to a concave up shape over here. But just there's nothing like along that line. It's just so smooth. Like it's nothing that really just pops out about that particular point, except we'd know there have to be an inflection point somewhere in this neighborhood. Concave down over here. Concave up over here. So we've done a lot of stuff related to curve sketching. We've done a lot of stuff that allows us to describe what's happening in a graph on different intervals. You know, I could tell you where something's increasing or decreasing. I could tell you where it has a max or a min by looking at the first derivative, or having the second derivative help me out with that. We can describe the concavity. We can identify inflection points. So what we're going to do now is kind of put all this together. And we're going to do one example together today about just how we start with a function that they give us, sketch its curve. And so what I often do first is just try to find any x or y intercepts. That doesn't require calculus. The y-intercept, I just need 0 to be in the domain, plug it in, get a point. If possible, if it's not like a huge undertaking, I'll get the x coordinates too, the x-intercepts too, setting y equal to 0 and solving. That just gives me some points to anchor. We're going to plot very few points when we sketch these curves. So we just have a few points that will kind of anchor our graph down, and then we'll just use what we know about the behavior of the graph to fill in the in-between spots. So I find those intercepts, and then I get all my information from the first derivative, like find critical values, figure out where the first derivative is positive or negative. And then I do the same thing for the second derivative. Where's the second derivative? 0, positive, negative. And I use that to fill in this table. So when I find the critical values in the places where the first derivative is 0 or the second derivative is 0 as well, like these constitute what I would call my points of interest. And I use them to partition the set of real numbers. So you know, suppose that my points of interest were like x equals -1, 1, and 3 or something, all right? Suppose there's 3 points of it all together between the first derivative and second derivative equal to 0. What I do then is I say, okay, on this number line, here's -1, 1, and 3. What I'm going to do is look at this interval, and then I stop and say what's going on at that point. Then I look in between, say what's going on in that interval, and then I stop and say, okay, what's going on just at that one point. Then I continue on and say what's going on here, and then stop and see what's going on at 3. And then last but not least, there's that last interval. So that's how I figure out what goes in this first column. So I'd have like -infinity to -1. Then I stop and see what's going on there. Then -1 to 1. Stop and see what's going on at 1. 1 to 3. Stop and see what's going on at 3, and then 3 to infinity. So even just a few points of interest gives you, quite a few rows here to look at. So a row for each interval, and I make sure I put them in order. This point here, like the first one where I'm just looking at f of x or the plain old y column, the given function, I only fill that in when we're stopping to see what happens at a particular point. and I just find the y coordinate there. Those give me some points to anchor down the graph. And then for the first and second derivative, all I'm going to do is write down, is it positive, negative, or 0? Positive, negative, or 0. Like the sign charts that we've been making, it's like I take that sign chart and I just sort of arrange it vertically down that way. And then I draw a conclusion. And that conclusion might look something like, I'm going to make up a number here. I'm going to make up or entries rather. Maybe my first derivative is positive and my second derivative is negative, so my conclusion is increasing concave down. Right? Just something simple like that. So once we make that table, we're kind of in a good position to kind of put it all together to make our sketch. And I want to do an example on the next page. So we could, let's see, we could just observe right now that it goes through the point 0, 0, like if x is 0, y is 0. So there's an anchor, the y-intercept is 0. So it goes through 0, 0. And I'm not going to bother with the x-intercepts right now. We found one of them, right? X is 0 is one of them. Let's get our information about the first derivative. So let's find y prime and critical values. And is it okay with everybody if I abbreviate critical value as CV? So here's my function. What's the first derivative? Minus 12. Am I ready to make a sign chart for this? What? No, why no? Yeah, we have to factor, right? So one of the biggest, like most common mistakes I see people make is they'll get to this point and they'll be like, all right, I'll make a row for 6x squared and I'll make a row for 6x, and I got to tell you that will never lead to a positive outcome. So we're going to factor this first. We're going to take out a 6, and then we'll see if we can't unfoil.
How do you know if you when to find the second derivative and when to just stop that? Is there a...
Oh, we're going to find the second derivative.
We are.
Yeah.
After we factor.
Oh, I mean, I'll still use this form.
Okay.
I'll just go back and be like, here's our first derivative. What's our second derivative?
Oh.
Yeah,
Okay.
yeah. Good question. Does this unfoil? What do we get?
X plus 2x minus 1.
Mm-hmm. So there's first derivative. That's the useful form to help us make a sign chart. So let's do it. You have a row for x plus 2. A row for x minus 1. I'm not including a row for 6. And the reason is because 6 is always positive. So it's not going to change the sign of whatever that product is.
Like that was like 6x, you would put that there for...
If it were 6x, I'd definitely put it there. I could just put the x, but yeah, yep. What are our critical values?
-2 and 1.
Mm-hmm. And since I know we're going to need them, let's go ahead and find the paired y coordinates. I'm just going to plug them into the function. So let's see, 2 times -2 cubed plus 3 times negative 2 squared minus 12 times negative 2 is 20. And if we plug in 1, we get 2 plus 3 is 5, minus 12 is negative 7. Okay. Those will come in handy. It was just sort of easier to go ahead and find them while we're thinking about those values. So the negative 2 and the 1 is what I need in the sign chart. X plus 2 is 0 and negative 2. It's going to be negative on the left, right? If I plug in something less than negative 2, if I plugged in negative 10 for x, then x plus 2 is still negative. It's going to be positive on the right. X minus 1 is 0 when x is 1. It's negative on the left side, positive on the right. And then we put these together to make our row for y prime. In this first interval, what's the sign? And in the middle? In the last one? Yeah. Now, I'm not going to draw any conclusions right now. I'm going to put that aside to say, we could look at that and say, oh, I know it's going to be increasing when x is less than 2. Like, great. We're actually going to use that information, but what I just wanted to do was just kind of organize that right now. And now we can move on to the second derivative. So let's find the second derivative and what I call possible inflection points, or PIPs. Because where the second derivative is 0 tells where you might have an inflection point. Remember, to actually have an inflection point, you need a change in concavity. So if that second derivative goes from negative to 0 to negative, it's actually not an inflection point. The concavity doesn't actually change. So the first derivative, I'm going to go back to this form of the first derivative because it's useful for me now. 6x squared plus 6x minus 12. What is the second derivative? 12x plus 6. And we could factor out a 6, I guess. 2x plus 1. So let's find where that second derivative is equal to 0. That happens only when 2x plus 1 is 0. And that means that x is negative a half. And again, since we're going to eventually need it, the y-coordinate is 6½ or 13 halves. There's one spot where the second derivative is 0, so this is a possible inflection point. But the sign chart should be easy to make. So I'm zooming out a bit so I can sort of just figure out how much space I've got. I've got decent space, I guess. Okay. All right, so negative a half. The second derivative is 0 there. If I plug in something less than negative a half, like if I plugged in negative 10 to this second derivative, what would we get? Positive or negative? We get a negative, yep. If I plugged in something less than negative a half, like plugged in negative 10 into the second derivative, will we get a positive or negative? Yeah. So this would be quite negative, right? I add 1, still going to be negative. Multiplied by 6, still going to be negative. If I plug in something bigger than negative a half, like 0, that's easy, it'll be positive. Okay, so y'all, we're ready to make this chart, this summarizing table, and then we're gonna sketch. This is great fun. You know something's fun when somebody has to tell you that it's fun. I kind of like curve sketching. I feel like I have to like take everything I know how to do to analyze a function and then do it all. It's so much fun. So I'm going to make this table. My first column is for just writing down what the interval or value is. Then I have a column for y, a column for y prime, a column for y double prime, and a conclusion. My points of interest between my first and second derivative, and I'm going to just write them in order, -2, -1/2, and 1. So I'm cutting up the real number line. My first interval goes from -infinity to -2. Then we stop and see what's going on when x is 2. Then -2. Then our next interval, what is it? -2 to -1/2. Then we stop. See what's going on at -1/2. Next interval. -1/2 to 1. Then 1. And then last. Yeah. Okay. I filled this in column by column. Like that is what I find easiest to do. The y column, like for the plain old function, we only fill that in on the actual numbers. And you'll recall we went and found those y coordinates as we encountered the x's. So at -2, we saw that y was 20. At -1/2, it's 13/2 or 6.5. And at 1, it was -7. The y prime, this is why I go ahead and make those sign charts. Because all I'm going to do, I'm going to zoom out for a minute. This sign chart that we made up here for y prime, I'm going to just take that sign chart, pick it up, basically rotate it like 90 degrees and just pop it down that column. I know that it's 0 at -2 and 1. And up here, in between the two, it was negative, and on either side, it was positive, or is positive. So negative, 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 positive, positive. There's that sign chart just arranged down that column. We'll do the same thing for y double prime. That was 0 at -1/2. It was negative on one side, positive on the other. Negative for the negative values, or for values less than -1/2. Positive for the values greater than -1/2. Now we're just going to go row by row and fill in our conclusions. In this first row, y prime is positive and y double prime is negative. What's our conclusion? Y prime is positive means what? The y prime doesn't tell us about concavity. It's increasing if the first derivative is positive. And what do we know if the second derivative is negative? Patrick? It's concave down. If the first derivative is positive, the function is increasing. The function is increasing if and only if the first derivative is positive.
And then the second one being negative says it's downward.
Says it's concave down. Yep. So like we could even draw a little sketch, like a part of the graph. Increasing concave down means that part of the graph looks kind of like has that shape. Now next, we're stopping to see what happens at -2. We know the first derivative is 0, so that means we could have a max or a min. Which one is it, and how do we know?
So min,
What?
it's a min
Why is it a min?
because it's concave down.
So because it's concave down,
No, it's max.
Oh, I see.
right, concave down is a max.
Yeah.
And now that is also consistent with, if we look at the first derivative, it goes from increasing to, down here, we're about to say it's decreasing. Right, so whether you look at this first derivative column on either side, or look at that second derivative entry next to the 0, you'll come to the same conclusion. These should always give you the same conclusion, and if they don't, there's an error somewhere. So yeah, that is going to be a maximum. Next row. First derivative negative tells us decreasing. Second derivative negative, concave down. At -1/2, that was our possible inflection point. Take a look at the second derivative on either side of that 0. What can we conclude? Is it an actual inflection point? Probably not a minimum because the first derivative is not 0.
It is an inflection point because it goes from decreasing to increasing.
Not decreasing to increasing. It goes from concave down to concave up, right? So inflection point is a change in concavity. So we have to look and see what's going on either side, because we see that change in sign, because there is a change in concavity. That is an actual inflection point.
So in which case would you have a 0 on your second derivative of y and then not be an inflection?
If the concavity didn't change,
Right,
so like maybe if my, so imagine, I'll tell you, hold on. Let's say y equals x to the 4th, all right? Y prime is 4x cubed. Y double prime is 12x squared. At 0, the second derivative is 0, but on either side of that 0, it's still concave up, because the second derivative will be positive regardless. All right, what's our conclusion in the next row? Yes. Good. What's going on when x is 1?
Minimum?
That's a minimum. And can you tell me how we know?
Because it's just increasing.
Right, so you can look for the change, right, to go from
Yeah.
decreasing to increasing. So that's definitely how we know it's a minimum. You could also see it's a minimum by looking at what? What does that tell us? Concave up, right? So concave up at a critical value also means it's a minimum. And then, excuse me, our last interval.
Increasing concave up.
Increasing, concave up. Okay. Now, this is the fun part. Are you ready for the fun part?
So,
Oh, wait. All right, so we're going to sketch this curve. If I look at my x values, my values of interest and stuff, and I guess had I found x-intercepts, I might include those as points of interest. I'm gonna let my x-axis just maybe go from -5 to 5. Like, it doesn't need to obviously go that huge, right? To kind of capture what's going on. And my y's though I need a little bit more space, so like I got to go all the way up to 20 for y and down to -7. So I'm gonna go up by like 2s. I'm gonna use a different scale. Then I'm going to plot my anchors. I already found that it goes through 0, 0. That was the first thing we did. We're like, oh, the y-intercept is 0. And then I'm going to plot these points here. Right, that we found. So, -2, 20, -0.5, and 6.5. Whoops. Maybe about there. And then 1, -7. I know that at -220 it's a max. So it's got to look something like that. I've got a min at 1, -7, so it's got to look something like that. And then I just have to fill in everything else. But that's what our conclusions are for. So let's take a look at this max here and just try to see what's going on before it gets there. We said that it's increasing concave down. It's increasing in this manner. And it's doing that all the way up until it gets to that max. There's an increase in concave down shape. Coming out of that, it's still concave down, but it's decreasing until it hits this inflection point, and then it becomes concave up. We're not going to notice a drastic change in the behavior. But it's going to still be decreasing and then heading into this min. So from -0.5 to 1, it's decreasing concave up. Then it heads out of that minimum in an increasing concave up manner. And then it stays increasing concave up the whole way. I know the behavior doesn't change in between, or I would have detected another change in signs of the first or second derivative. But we made our sign charts. We know that nothing different happens. So there's the graph. How fun is that?
There.
Yeah. Isn't it great? It's not just for a little graph. It's a lot of work. It's the goal. The graph is a proxy for like understanding the behavior of a function. Right? That's a stand-in. If you can graph what a function looks like, that means that you've done a lot of work to understand what its behavior is. And we're able to tell that by plotting very few points. And I know without a doubt that it doesn't turn around again, or I would have found it. I know the concavity doesn't change from here on out, or I would have found it. Right? Like, there's a lot of confidence, and I know exactly what happens there, even though I had not plotted a single point beyond x equals 1 or below x equals -2, and I still know that's the behavior of the graph. That's it. I can have confidence in like what the behavior is on the whole real number line by just examining what it's doing around here. Cody.
This may be a silly question. I think it probably is. How does -1/2 and 6.5 like visually an inflection point there?
Oh yeah, so it's not a stupid question, but like So sometimes inflection points are really noticeable and sometimes they're more subtle. I mean, I would call this a pretty subtle inflection point. We know, like, from here, we can tell obviously concave down, obviously concave up. So it's got to change somewhere. This is where it happens. It is pretty subtle change in behavior.